Good morning. Today we're going to talk about hypothesis tests. Hypothesis test is one way that a scientist can test the assumed validity of some population parameter. So for example, maybe scientists have always thought that the true mean number of hours that people exercise each week is 7, but you think it's higher or you think it's lower based on your own research. How do you test the initial claim? Answer, using a hypothesis test. Or maybe some people think that 30% of Americans hate mustard. This is based on lots and lots of data. But times have changed, people are warming up to it, and you're thinking, as a social scientist, I think more people like mustard than that. How do you test the claim? Answer, hypothesis test. The way a hypothesis test works is you have some sort of assumed parameter value. So for example, somebody assumes that the true mean is 10, and what you do is you go out and you collect a sample. So if the assumed true mean were 10, and you collect a sample, then you're going to get some sort of X bar from your sample. You're then going to compute what's the probability of getting your sample or something even larger. Again, I'm writing greater than, I just said, or larger. Doesn't matter because this is a continuous distribution. You could write greater than or equal to. So you're going to ask, what's the probability of this happening? And in parentheses, if mu really is 10. You're going to compute that value. How will you compute it? You'll compute it with the help of the central limit theorem. And either a z distribution, if sigma is known or assumed, or a t distribution, if it's not, is lurking behind the scenes. So you compute this probability, and let's say you get a very, very low value. Question, if you get this, what do you conclude about mu really being equal to 10? Pause the video, think about that. Well, hopefully you say, well, gosh, somebody's telling me that mu is 10. I go out there and I get 13 as an X bar. I compute that the probability of getting this, if mu really is 10, is really low. So guess what? I don't believe this. I'm going to reject the claim that mu equals 10. I don't believe it. Now, a couple of points about that. First off, we have to define what we mean by really low. Maybe for some of you guys out there, this isn't low for whatever reason. So we need to define what we mean by low. We need to come up with a cutoff value, and that's going to be called the alpha level of the test. Second, let me also say that, you know what? Even if this is crazy low, it's still possible if this really is 10. So hypothesis tests, just like any other aspect of statistics, are not foolproof. You could come to the wrong conclusion. Okay, so that's just a verbal overall picture of hypothesis tests. What I'd like to do now is write out an example, go through that example over here, and there are going to be some kind of notes and nuances that I'm going to put over here to generalize the process. Because once you understand one hypothesis test, you can do any hypothesis test. The only difference between hypothesis tests are the thing that you're testing and your test statistic. So testing the mean, your test statistic might be some sort of z or t distribution. Testing a proportion, it's going to be a z distribution. We'll cover those this quarter, but in the future, you can also test the true variance. You can test the difference of means, a difference of proportions. The process, the underlying vocabulary is going to be exactly the same. The only difference, again, is going to be the thing that you're testing and the test statistic. So let's get started with an example. So example, let's say someone claims that college students sleep an average of 8 hours a night. You're thinking to yourself, no way, impossible. You think it's lower. From a sample of 50 college students, you find sample mean X bar of 7.2 hours per night. Probably thinking that's still way too high, but that's all right. If we assume that the true standard deviation is, let's say, 0.4, what do you conclude? At the 5% significance level. Okay, so there's a little bit of new vocabulary in there. We'll talk about that. So let's see. Somebody claims that college students sleep an average of 8 hours a night. You think it's lower? From a sample of 50 college students, you find this guy over here, 7.2, and you make the assumption that sigma's 0.4. What do you conclude at the 5% significance level? Okay, so we'll get to this in a second, but let me just say the first step of any hypothesis test is you want to mathematize it. You want to turn it into symbolic form so that we can do some computations. And the interesting thing is once you put it into symbolic form, it doesn't actually matter what the topic is. College students sleeping a mean number of blah, or I don't know, 50-something women running an average of blah hours per week. It doesn't matter. What matters is what the thing that we're measuring is. So we're measuring an average. Okay, so again, the first thing we're going to do is we're going to mathematize this thing. So let's look at this first couple of sentences. We have a claim about something. So somebody claims that this is true. And the way that we're going to write that is we're going to write that H naught is that mu equals 8. So this is read as H naught, mu equals 8. This is called the null hypothesis. This is always the thing that is currently assumed. You think that it is lower. So this is what you're thinking. And that's H sub 1. It also goes by H sub A for alternative. You think it's lower. So the alternative hypothesis is that mu is less than 8. Okay, and then you could also, again, write it as H sub 1 or H sub A. So let's see. So let me put a couple of notes about this then. So let's kind of visualize what's happening here. So somebody is making the assumption that it really is 8 hours. So if we were to draw a picture with this, somebody thinks that the true mean is 8. Okay, I'm drawing X bars distribution. Somebody thinks it's 8. And you think it's actually lower than 8. So you found that X bar was 7.2. So what we're going to do is we're going to compute the probability of getting something that we got, which was 7.2, or something even more extreme in that direction. We can't just compute the probability that X bar is 7.2 because that's going to be 0. We're going to compute this probability. Now, I have to be honest, I'm not sure where it is on the axis this way, but we're going to be able to compute this using the numbers given. And per my initial discussion, if that probability is low, we're going to reject the null hypothesis. Okay, so a couple of notes before we continue with this. We're performing what's called a left-tailed test. The reason for that is we're using this probability on the left side. If we had asked, or if we thought that mu was bigger than 8, then we'd be performing a right-tailed test. And each of these guys falls under the broader category of a one-tailed test. So for each of those, we're testing one tail. Another thing that we could have tested, or something that we might have been interested in, is saying, hey, I just don't think it's 8. I don't know if it's higher or lower. And sometimes you're just interested in that. I mean, think about it. If you have some sort of machinery that's supposed to, I don't know, put some liquid in a can, you are part of quality control. You just need to test whether it's really putting in 8 fluid ounces or not. If it's not, you got to recalibrate the machinery. So in that case, we would have H1 is that mu is not equal to 8. And this is called a two-tailed test. So visually, in this first case, we would do this one-tailed test if we got some value out here. Maybe we got x bar is 8.3. And we would reject the null hypothesis. If we got a small probability to the right of our x bar. For the two-tailed test, we still might get 8.3, or we might even get the 7.2. But basically, we would reject if this probability is too small, but we have to take into consideration this side in some regard. And we'll talk about that in a couple of minutes. Okay, so here we're concerned of whether this is too small. Here we're concerned whether this is too small. Here we're going to do some sort of symmetric computation. Okay, so back to the information that we have here. Let me continue mathematizing it so that we have the information that we need, no more and no less. Okay, so from a sample of 50 college students, okay, n equals 50, you find that x bar is 7.2. Assume that sigma is 0.4. What do you conclude at the 5% significance level? Okay, so as I said in the introductory portion to this, we need to determine ahead of time what too small is. Remember with that 0.0001. We need to come up with a cutoff. In the same way as when you take a class, you need to know ahead of time that 60% or 70% means you pass the class. I shouldn't say this on video, but that's somewhat arbitrary. I mean, I could say 85 is passing the class. Doesn't matter what someone says, but once they say it, that is the cutoff. So this 5% significance level is also called the alpha level. The alpha level of a test, and this is our prescribed cutoff. So in other words, once we compute the probability, if we get a value that's less than 0.05, we will reject the null hypothesis. So, a probability less than 0.05 means that we're going to reject the null. We're going to reject this claim. If it's bigger than 0.05, we won't reject the null. So this is our cutoff point. All right, so how are we going to do that? So let's see. Well, from this 0.05, let's actually draw the picture. Once again, so here's the 8. So I said that if I get something that's too low, then again, I'm going to reject the null. So why don't, originally what I did is I sketched in the probability of getting less than that value, which is going to have its place. But instead of doing that, let me actually sketch the this region where we reject. So again, there's some point here. There's some point here where we are going to reject, so that anything to the left of this, we're going to reject the null hypothesis. So this region where we reject is called the critical region. It's the rejection region. So if we get any value less than this thing, we're going to reject it. Well, this is a little bit tough to compute as it is. So you know what I'm going to do? Instead of doing x bar, I'm going to compute that value using my standard normal distribution. This is something that we did a long time ago. In fact, I mentioned that z sub alpha would be an important concept later on. You'll have to go back to your normal distribution lecture to see that. And this is actually where it's finally coming up. We're looking for a z sub alpha on this side, on the left side. So how am I going to get that? Well, that's just going to be my DISTR, INV norm, 0.05. And we get minus 1.645. So this is minus 1.645. So the way that I'm characterizing this now, again, this is a standard normal, this is z, is that if this guy, when translated into a standard normal, if it's less than minus 1.645, if it's over here somewhere, then I'm going to reject the null hypothesis. So how do I convert this to a standard normal? The central limit theorem. So we want to take x bar, 7.2, minus mu. Well, what's mu? Mu is assumed to be 8. We're assuming it's 8. Over sigma, over the square root of n. This is going to give us a z value. If this z value is less than minus 1.645, we will reject the null hypothesis. So let's check that out. So the top is minus 0.8. Let me multiply it by square root of 50. So I'm just flipping the bottom. Times 0.4. And we get minus 2.26. So the question is, what do you conclude? Do you believe this or not? Well, hopefully you said you don't believe it because you got minus 2.26, which is out here somewhere. That's less than minus 1.645, so it lives in our rejection region. It lives in our critical region. It's far away from the mean, as we're defining it. Far away is this minus 1.645. Therefore, we don't believe this, and we will reject the null hypothesis. Okay, in this case, we're going to reject the null. So this is evidence. Evidence, another way of saying this is that it's evidence that the true mean is less than 8. So notice I didn't test that it's equal to 7.2. I'm testing whether it equals 8 or whether it's less than 8. And this is evidence that it's less than 8. Let me also say that there's another thing that you can do with this minus 2.26. Because if you think about it, you know, this minus 1.645, this alpha level was pretty arbitrary. With that said, typically with tests, you'll see 1%, you'll see 5%, but there's still an arbitrary value to somebody deciding that, oh yeah, this is what I think unlikely is, anything below 5%. So what we can do is we can compute the probability that z is less than minus 2.26 so that we can actually get a value for that probability. We can actually specify exactly how unlikely this is. And that we're going to use our good friend normal CDF from minus infinity, or again, minus 10 to that value. So before you do that, you should be able to tell me an upper bound for that value. You should be able to do that without using a calculator. So hopefully you said, oh, this is definitely less than 0.05 because this z value is over here. And if you look at the area, that's going to be smaller than 0.05. And in fact, I get 0.0119. This value that we computed here, this guy, so it's the same thing that we did here, this is called the test statistic. It's an easy value to compute, but I invite you to pause the video and say test statistic 5 times fast. Incredibly difficult. All right, hopefully you give that a shot. Let me also say that this guy here is called the p-value. It's called the p-value. And the p-value is the probability of getting our value or something more extreme. Probability of getting our value or something more extreme. And the way it's being defined here, I'm going to bring something else up, which is a nuance with the two-tailed test. So if we had a two-tailed test, what you do is if your alpha level is 0.05, you're going to take that probability, which is the entire probability of the unlikely region, and you're going to need to split it into 2 parts. So you'd have 0.025 here and 0.025 here. So if this were a two-tailed test, then what you do with the p-value is as follows. So let's say you do get the probability that z is less than minus 2.26. Let's say you get 0.0119. Well, what you're going to do is to get the p-value in this case, to be fair with the fact that we're living in both sides, is you're going to double this value. So this is not the p-value in a two-tailed test. For the two-tailed test, you're going to use twice that as your p-value. Because again, in the two-tailed test, you're defining more extreme to be either lower in that end or higher in that end. So we're taking our 0.05, we're putting into both tails, so you just want to be analogous with what you're doing with your p-value. All right, so let me summarize some of the vocabulary that we looked at. I know this is a video, you can always rewind. But the main ideas are to mathematize, that's the first thing. We talked about the alpha level. So the alpha level, again, is how we define what we mean by unlikely. We talked about the p-value. This is the probability of our sample for something more extreme. We talked about the idea of one-tailed, two-tailed tests. And hopefully you realize that to work through these problems, picture is super, super helpful. Yeah, I would never do any of these without drawing a picture. We talked about the test statistic. And what this is, it converts our data to a distribution. So I just did an example here where we were testing the mean. If sigma is known, well then your test statistic is going to be x bar minus mu over sigma over root n. Because that's how we can convert it into a probability, or something that lives on a probability distribution. If sigma is not known, it's the same exact process. The only difference is now my test statistic is going to be x bar minus mu over s over root n. I'm going to use a t distribution. So this guy's a z, this guy's a t. Finally, we came to a conclusion. So if the p-value is less than the alpha level, then what? Do you reject the null hypothesis or not? Well, hopefully you say, yeah, you reject the null hypothesis. Because the p-value is the probability of getting what we got. The alpha level is the cutoff level for what we consider to be unlikely. So if we get something less than that, we're going to reject the null hypothesis. Otherwise, so let's see. If we don't reject the null hypothesis, there are actually two ways you could say it in English, right? If I don't reject the null, I could say that I accept the null. I'm going to put a question mark. Or another way I could say it is I fail to reject the null. Fail to reject H naught. In English, maybe an analogy would be saying, I think you're right, or I don't think you're wrong. I've seen both of these. Typically, maybe in sciencey type class, they might say something more like accept the null. I learned it as failing to reject the null, and I actually think that makes more sense. The reason I think that makes more sense is if you say that you're accepting, if you're saying that you're accepting the null, then to me it's saying that you're not leaving any room for doubt. I think you're right. This one, again, is analogous to I don't think you're wrong, but there's a little bit of doubt in there. And hypothesis tests, again, are not 100% foolproof. You are only collecting a subset of your data from the population. So there's no way you can be 100% certain with the hypothesis test. That's why I think this is better language. I'm not going to make a deal out of it in a testing situation, but I think it would be great if at least for this quarter, you use the fail to reject language so that in future quarters, you're saying to yourself, even if you wind up saying accept, in the back of your mind, you're saying, ooh, well, yeah, I'm accepting it, but I could have made a mistake about this in terms of what conclusion I'm drawing because of the randomness of the process. All right, that's all I have to say about hypothesis tests. In the next lecture, we'll look at hypothesis test for a proportion, and you'll see that it is exactly the same process, the only difference being that we have a different test statistic. Thanks for listening, and I will see you next time.